to Canvas. My YouTube channel. All right, here's Shelby.
Hello, everyone. How are y'all this morning? I'm good. How many of y'all have heard of Student Support Services at Texas State? Nobody? Okay, great. I'm glad I'm here then. So we're
last week.
yeah, maybe you typed your notes. But anyway, I am grant coordinator at Student Support Services. My name is Shelby Sneed. If you go to Student Support Services on Texas State, you can find my profile if you want to reach out for any reason. But basically, we're an organization that helps any class of student, freshman, sophomore, junior, senior. You just have to be first generation, low income, or registered with the Office of Disability Services. And then for STEM specifically, you need to have a major in the College of Science, Technology, Engineering, or Math. If you're not a STEM major, there's SSS, like the traditional one that you can also apply to. This QR code, and it's also on this little thing, which I'll leave up here when I leave. If you scan this, you can just apply. It's an easy application. You should get accepted pretty soon, as long as you're one of those 3 qualifications I mentioned, which is listed on the flyer in your announcements and on these physical copies if you want to grab one. As long as you meet one of those requirements and you're accepted, you're going to have access to one-on-one coaching. You're going to have access to one-on-one tutoring, early registration next semester. That's a huge deal, right? We have workshops with cultural programs. It looks good on a resume, helps with classes, even if it's not like a STEM class that you need help with. We have tutors in every subject. So yeah, financial aid guidance. I just sent out an announcement this week about a scholarship. That's part of my job, is looking for scholarships and letting the members know about them. So, and then the STEM specifically, we have a scholarship we give out, I believe last semester or last year, it's open in November. Everyone that applied, I think, was awarded money. So, because we don't have enough people applying. So please apply. You're almost guaranteed a little bit of money from that. And that's only for STEM. So yeah, does anyone have any questions about that? No? But yeah, you have this, I believe, in your announcements on your Canvas page. If you want that QR code, if you want to grab this, I'll leave it up here with Dr. Irvin. So yeah, if y'all don't have any questions, thank you for letting me take some of your time.
Thank you very much. Yeah, and for those of you at home, of course, you can find this flyer on the Canvas page, so it's easy to find. So I highly recommend, if you're one of those groups, because it is a new service, and therefore it's good to kind of get in on the ground floor of it and be able to do that. Okay, so what we're going to do now is we're going to shift over to my laptop, my iPad here. And that's the wrong one. Preparing for the final. Okay, so the first thing I'm going to do is I'm actually going to go backwards. I'm going to start at chapter 11 and work my way backwards, because we have our next exam over chapters 8, 9, 10, and 11. Okay. So what we'll do is we'll review those first. This is for the final, but this is all the topics of all 11 chapters. Now, I also have a list of topics for this exam on Canvas. It's under resources. It's called chapter quiz 5 topics. Make sure you've studied all of the topics on this list right here, and I'll go over it today as well. So our final exam is coming up. It's both for this class and my other class. It's on June 9th.
You mean May 9th?
I'm sorry?
You mean May 9th?
I meant May. Yes, I'm sorry, May 9th. Yeah, June 9th, I'm going to be in St. Thomas, no, St. Martin. So yeah, May. I'll correct that. Okay, and it says this on our schedule of exams, etc. So our other exam is on May 2nd. So we have Monday, May 2nd for our exam over 4 chapters, and then our Monday, May 9th for our final. It will be the ACS exam. So if you have already gotten your ACS study guide, that's a good place to start. And now the book's divided up through first term and full class. So look for the first term stuff, okay? There are typically none of the above on here. You only get 4 choices, A, B, C, or D. So you can usually eliminate one of them or something and do that. There are 70 questions, and you should answer all of them because it doesn't count against you. It only counts, for you, because we're taking, the number of questions you get right. So even if you get it down to a 50-50 shot, answer all your questions. You will be provided an exam book, a lecture, an answer sheet, and scratch paper. Now it's going to be one of the big ones, the big Scantrons, and you're going to bubble your name into it. So you want to bubble that as you go. And you have to turn in everything. One of the things I'm going to have you do is you have to bring a photo ID or have it on your phone, a photo ID of some sort. And you're going to need to write the exam number on your Scantron, okay? Because then we can make sure that all the materials get back. If somebody absconds with an exam, that's an immediate F in the class, and it's going to be, there's a very high penalty for it apparently. And if we just lose one, it's like $150,000 to replace it. So we count them twice and 3 times, 4 times. Anyway, so you'll have an hour and 40 minutes to take it. Use all the time you need. If you have ODS accommodations, you want to take it at the testing center because there's a class right after this, and there won't be time for me to give you time and a half. So make sure you go to get that scheduled on testing center. As long as it's on the same day, they'll handle your extra time. Make sure you understand the question. On that last quiz, I asked things 2 ways, backwards and forwards. And so I wanted to make sure that you are reading the question carefully. So I haven't actually graded them yet. So I'll do that tomorrow morning, sorry. Let's see, read all possible answers and make sure that you don't only pick the one you think is right, but you know why the others are wrong. Okay. So that's a good way to do it. The way I was showing in the homework about trying to get as close as you can, or the way I've talked about strategy if you come into office hours, talking about look at the question, here's a strategy, whatever that has, like that. Okay, bubble as you go. If you study really hard but you don't recognize the reagent, it's probably not one. It's probably not the one. If you didn't study hard and don't recognize the reagent, well, that's a time management problem on your part. So you should see that. And if you have not filled out your reaction table, this is the time to do it. Because your reaction table, you will recognize a lot of reagents this way, and you'll know where they go. Okay. So what I'm going to do, and the rest of it is I'm just going to kind of give a summary of some key concepts. You should recognize all of these key concepts, and anything that looks a little hinky, you might want to study up on. Okay. So, and then the Luthra. Oh, yeah, sorry. That's the car company. I'm renting my car. Anyway, so you can look at your final grade. We're probably going to have about a 30-point. There's typically a 25 to 30-point curve on it, and it's going to be a flat curve. It's not going to be a Gaussian curve. So we're going to just do it that way. And then I'll send the exams to the testing center, and so it's going to take a couple of days to get it back. So look for that by Wednesday. All right. Questions about the exam and the exam format? Good. Okay, so the third exam will be the same format we have. And so, and there is a partial periodic table in the exam booklet, but then there's also the 2 on the wall. So right here. Okay, so like I said, I'm going to actually go backwards. I'm going to start with chapter 11. No, okay, I'm going to read off the stuff on the flyer on Canvas here. So in chapter 8, we learned all about addition reactions, right? So we're taking a double bond and turning it into 2 sigma bonds. And we had a bunch of different reagents to do that. You need to know these reactions 3 ways: the substrate reagent and figure out what the product is, the substrate and the product and figure out what the reagent is, or the product and the reagent and figure out what the starting material is. Luckily, in the addition reactions, your starting material is always a double bond, okay? And so then know that they have regio and or stereochemical assignments to them. Markovnikovs, anti-Markovnikovs, the anti-addition, syn addition, okay? Know that when you make a carbocation, you get a mixture of syn and anti. Know that when you have something on top, it has to be anti. So mercurization, demercurization, bromine, or chlorination are anti. So know these things. Know how to make a diol by both osmium tetroxide and cold potassium permanganate. And then know that you can cleave your double bond. And if you want an aldehyde, you can cleave it with ozone. If you don't care and it can go down to ketones and carboxylic acids, then you can use hot potassium permanganate. And then a reaction, know that the reduction and the cis-trans selectivity of alkenes, alkynes. Know the cis-trans that you can get from either nickel boride or Lindlar's catalyst. You get syn addition, therefore cis alkenes out of them. And you have dissolving metal reduction to get the trans alkene. And if you don't use either one, you just get an alkane. So it's easy. All right. Chapter 9, spectroscopy. You only need to know 4 things in proton NMR. Number of signals, position of signals, integration of signals, and spin-spin coupling or splitting. Carbon NMR, it gets simpler. You only need number of signals and position of signals. Okay, and know those kind of map out. There's 2 charts in the book that kind of map out where those things are, knowing their general areas. And then there's 4 things you need to know about mass spec. The molecular ion peak, the base peak, the relative abundance, and the fragmentation patterns. But you also want to know your isotopes, because nitrogen rule, if it has an odd number mass, it's going to be a nitrogen, odd number of nitrogen. Know your bromine isotope peaks, your M and your M+2 for bromine and chlorine. Okay, questions about spectroscopy? Okay, radicals. Radicals only do 2 things: hydrogen abstraction or add across the double bond. Radicals also have 3 steps: initiation, usually with a peroxide. Then propagation, where you're always creating another radical, either through hydrogen abstraction or through it reacting with some neutral species. And then termination. And so there's a lot of, anytime you have a radical-radical coupling, you're going to have termination. Okay. Know that peroxides are used and why they're used. Okay, I shouldn't have done that. Come on. There we go. All right. Let's see. Know the reactivity and selectivity. Okay, bromine is less reactive than chlorine, therefore it's more selective than chlorine. Know the relative stabilities of your radicals, because that's going to lead to selectivity and location. Anti-Markovnikovs with HBr. It adds Markovnikovs without peroxides. It adds anti-Markovnikov with peroxides. And know that you have allylic and benzylic radicals that are even more stable than tertiary radicals. And that is analogous to carbocations. Okay. Questions on radicals? Yes.
So if you're using a peroxide and that peroxide becomes a radical, that's part of initiation, correct?
Correct.
When that radical goes and let's say it turns a carbon, like makes a carbon radical, does that count as propagation or initiation?
So let's see. When the radical abstracts a hydrogen to generate another radical, that's propagation, because you're starting with a radical and finishing with a radical. Initiation is no radicals, radicals. Propagation is radical, radical. Termination is 2 radicals, no radicals. So that's how you can tell the difference between the steps. Okay? All right. So the last thing we have is the alcohols chapter, nomenclature. You're gonna and study your nomenclature. Is somebody's dog coughing? All right. So you're not muted, by the way. Okay. Anyway, okay. So know about hydrogen bonding, boiling point, and water solubility. That's in the book. If you hydrogen bond, like dissolves like, you can review that in chapter 2, as well as it's in the book for chapter 11. Made by reactions, know how to make alcohols. Chapter 6 with substitution reactions. Chapter 8 with addition reactions. Reactions with HCl, HBr, and HI. Know that you can turn them into alkyl halides. But know that the chlorine doesn't work very well on primaries, and you have to use a Lewis acid catalyst, zinc chloride. Know that you can also convert it with PBr3 and SOCl2, thionyl chloride and the phosphorus. And remember, we're making the oxygen a better leaving group in all these cases. The sulfonate esters, we're making oxygen a better leaving group in that case as well. Williamson ether synthesis, it's a substitution reaction, but you have an alkoxide and an alkyl halide, and you want to have the least substituted alkyl halide as possible when you do it because the reaction will run faster. Protecting groups, the T-butyl ether and the silyl ether, so that we can protect, react, deprotect. And then the epoxies. There's two ways to make them, with a per acid or with an ether synthesis. So you have to have that halohydrin to do that. And then the reactions with a good nucleophile, it gives you the least substituted alcohol. But if you add acid, it changes the catalyst, changes the mechanism, and you get the alcohol on the more substituted side and the nucleophile attacking at the less substituted side. Okay, so no, that's the other way around. Without acid, you get the alcohol showing up on the nucleophile hits the least substituted side. With acid, the nucleophile hits the more substituted side. Sorry, do not, yeah, that was correct. Okay, so that is chapter 8. Okay, any questions? I mean, that was chapter 11, sorry. Any questions on that? So these topics are listed on there, and of course, there are a couple things that are in the book, like hydrogen bonding and solubility, that will need to be looked at. So let's go ahead, and I'm going to start back at chapter 1. Okay. I've harped on the hybridization quite a bit, okay? Because hybridization changes shape and shape changes hybridization. So you look for both of those. And so we want to look at that. So it all goes back to your Lewis dot structure. I would also kind of don't write in the book itself, but if you remember that there are lone pairs places, you might help you figure out what's going to happen. Okay, so your Lewis dot structure is important. Knowing about those lone pairs is very important, and it tells you about your molecular shape, right? All right. You will be doing formal charge calculations on the final, so you might want to know how to do that again. Again, it's valence electrons minus all of the non-bonding electrons, most of the time lone pairs, and half of the bonding electrons, because it's shared, okay? So know that. Number of bonds in a neutral state, that's just saying that it makes it easier to figure out that hydrogen and halogens only bond once, carbon bonds 4 times, nitrogen bonds 3 times, oxygen bonds 2 times. So knowing those things will help you out. And then know your hybridization and your shapes. Tetrahedral, trigonal planar, and linear. Okay. Questions on that? Okay. So when, as you're studying, just keep doing a running tally in your head about the different shapes of things. Okay. All right. So let's look at some geometry of some common intermediates we have right here. We have the carbocation. Carbocation is sp2 hybridized with an unhybridized p orbital with 0 electrons in it. So that way your electrons can come from the top or the bottom. Okay. Radical is also sp2 hybridized, but it has 1 electron, 1 unpaired electron in that p orbital. And as soon as that starts to form a bond with another radical, it hybridizes to sp3 and get your tetrahedral product. And then we actually created an anion during the dissolving metal reduction. And it's also sp. It tried to be sp2, but it can't. It's got 2 electrons. And so it's actually sp3 with 2 electrons in that hybrid orbital. Okay. So the radical and the carbocations are sp2 hybridized, and the anion is sp3 hybridized. And then, of course, if you look at your lone pairs, your oxygen is going to be bent because of the lone pairs. And so our water is bent because of the single lone pair on nitrogen. It's tetrahedral in electronic configuration, but trigonal pyramidal in shape. And then, of course, we have our nice tetrahedron, which is our nice, fully sigma bonded center ion. All right, questions on shapes and hybridization? Okay, so there are many, many ways to represent a chemical compound. There's the condensed structure. A lot of these things are going to be written out that way. Okay, and there's also the Lewis dot structure, which of course will help you identify where the lone pairs are in the shapes. But then we also have our skeletal structures like this right here. And that's going to be a very common one. But if we need to know stereochemistry, we need to do our perspective formulas. Probably not going to run into any ball and stick, but you should know what it represents at least. And then, of course, our Newman projections and our Fisher projections. Those tell us a lot about which thing is going to be more stable. Okay, Newman and Fisher projections. Okay, and then our Fisher especially helps when you have more than one stereocenter. Okay, questions on representing organic compounds? Okay, all right, resonance stabilization. So we're looking for, in all of the cases with resonance stabilization, we're seeing that we can draw valid Lewis dot structures, right? And it could be here or it could be there. And we could have a charge on one atom or a charge on another atom, okay? And the rule is the more stable one is where your negative charges are on the more electronegative atoms, and your positive charges are on the more electropositive atoms, the less electronegative atoms. So you want to make sure that you're doing that. When we have delocalized electrons, think of the acetate ion. The charge goes back and forth. Think of the, let's see, benzylic and allylic radicals, the benzylic and allylic cations. Those are going to have those delocalized electrons. And then our resonance hybrid is that thing where you're going to have partial charge and partial bonds. So we're going to represent it as this. And knowing that, okay, oxygen is a little more electronegative than nitrogen, so there's going to be a little more of a negative charge on the oxygen. So that's going to be this one is going to be slightly favored in its resonance structure, but the hybrid is still valid with partial charges. Okay, so note that you have all your different resonance contributors, and know that if you have more than two, you can have 3, 4, 5, but they're probably not going to be all equal in energy. One of them is going to be a major contributor. In this case here, it's going to be pretty close, but this B is going to be just slightly favored. In the acetate ion, it's an oxygen-oxygen, so all the resonance, all contributors are equal. They're all equal. All right. So questions on that? Okay, so when we have our resonance contributors, we want to look for things with an incomplete octet, because the incomplete octet is going to be less stable, right? Negative charges on the most electronegative atom, positive charges on the least electronegative atom. And then look for charge separation too. In this case here, we have a resonance structure here, and with no charges in here, it's the most stable configuration, right? And then we can get this over here. We have a positive charge on the more electronegative atom and an incomplete octet, making it less stable. And in this one here, we have the negative charge on the electronegative atom and the positive charge on the less electronegative atom. So that's okay. So this is actually going to be more stable than this one, but they're still all resonance contributors, which means there's going to be a partial negative charge here, partial positive charge there some of the time, but they kind of cancel out because in this one, it's a partial positive and a partial negative. So we're looking for that in our system. Okay. Okay. So that's chapter 1. Okay. Your shapes, your resonance structures, your stability trends. All right. In chapter 2, you need to know all the functional groups on chapter 2, the table in chapter 2. Okay. I know we only went up to alcohols this semester, but it's going to be, things that are going to be there. Understand the electronegativity and polarity trends on the tables, and net dipole right there. Net dipole gives us polarity. And intramolecular interactions. The stronger ones like ion-ion or a covalent bond are not. Those are intermolecular. We're looking for intramolecular. And then we go to the intermoleculars, which are the induced dipole, weakest, dipole, which is slightly stronger, and the hydrogen bond, which is stronger and has the greatest influence on the boiling points, right? If the more hydrogen bonding you have, the higher the boiling point is. Which structural features give rise to which types of interactions? Ketones are dipole-dipole. Alcohols are hydrogen bonding, etc. Okay, and the effect of that intermolecular interaction on properties. Now, we did it once in chapter 2, and it's in the book again in chapter 11, talking about the hydrogen bonding of alcohols and how it affects their thing. It affects melting point, boiling point, and solubility. Solubility, like dissolves like. So if it has something hydrogen bonding, it's going to prefer a hydrogen bonding solvent. And the more interactions you have, the more it influences the boiling point and melting point, the more it raises them. Okay. So things that you should consider when deciding which of these compounds is going to boil higher. You're looking for interactions first, if they all have the same molecular weight, okay? So if they all have the same molecular weight, then you have to look for something more. If they all have different molecular weights, the higher the molecular weight with the same type of interactions, the higher the boiling point, okay? Hydrogen bonding increases boiling point more than anything else. Polarity will play a role. If you don't hydrogen bond, polarity will increase your boiling point. Branching decreases boiling point because you have less surface area for it to induce dipole. So the more spherical they are, the fewer interactions, and the lower the boiling point. And pressure. You can actually make something boil at a lower boiling point by reducing the pressure, pulling back too much. So here's an example right here. These are all slightly about the same molecular weight. They're all about the same molecular weight. And we have only induced dipole, and it has the lowest boiling point right here. And by adding one carbon right here, you've changed it and increased the boiling point. In this small ether here, we have it boiled below again, this only has a dipole. By adding a carbon, it raised it about 30 degrees. Okay. With this nitrogen here, this is a weak hydrogen bonding, but it has hydrogen bonding, so it increased the boiling point. Adding a carbon increased the boiling point again. And alcohol, of course, is our best hydrogen bonder with the highest boiling points. And again, adding a carbon still changes it. So molecular weight as well as the type of interaction you have. So look for molecular weight. And then type of bonding. And then there's also the branching is a subtlety, but you should remember that as well. In addition, you may have noticed in lab that when you mixed two components together at a mixed melting point, you actually got a lower melting point. So impurities actually lower them as well. All right, so solubility trends, likes dissolve likes, alcohols dissolve alcohols, ethers dissolve ethers. But after a while, you can have your hydrogen bonding structure like an alcohol. You can pull in about 5 carbons for every alcohol. And then after that, it starts getting less soluble in water. So if you have a 10 carbon chain, you need 2 alcohols on there to get it completely dissolved in water. Okay. So Up to 4 carbons are soluble in water, and then that 5th carbon makes it pretty much very poorly soluble. A little will go in. Ethers, up to 3 carbons in water, because the ether only has the dipole interaction and the water has the hydrogen bonding. Amines, primaries are more soluble than secondaries, which are more soluble than tertiaries. Because in the primary, it has 2 hydrogens. In the secondary, it has 1 hydrogen to hydrogen bond. In the tertiary, it has 0 hydrogens to hydrogen bond. So it means the water is just bonding to it, and it has a dipole moment. Okay. Alkyl halides, the alkyl fluorides can hydrogen bond, so they tend to be most soluble in water, but the rest of them above, just a couple carbons and they're insoluble. Okay. Let's see. Yes.
And how can alkyl fluorides hydrogen bond?
The fluorine actually, turns out fluorine is so electronegative that it can be hydrogen bonded to. Just like the hydrogen bonds usually go for the lone pairs on oxygens and stuff like that, it actually will do that to fluorine as well. Okay. All right. Then the next thing is chapter 3. Know this table right here. Because, I mean, it's just all the different types of groups there that tell us why we have it. We have carboxylic acids, most acidic because of resonance. We have phenols that are more acidic than regular alcohols because of resonance. Then we have alcohols, which are about the same as water. And then we have the alkynes, the amines, alkenes, and our weakest acids are sigma bonds with carbon. Okay. Know the trends that are in there. Electron withdrawing groups make things more acidic, but it's a through bond interaction. So as it moves away from the acidic portion, it is influenced less and less. Okay. Resonance increases our solubility, our acidity. That's why these are the more acidic ones. And the carboxylic acid and the phenols are more acidic because they are the ones with resonance. The 4 things that affect our thing is the element, right? Electronegativity and size. Electronegativity and size. Okay. Hybridization. Alkynes are more acidic because they're sp. More S character makes it more acidic. Resonance. And then inductive effects, inductive through bond effects with electron withdrawing or electron donating materials. Okay. And let's see. The hybridization versus electronegativity. More S character means more acidic. Our alkynes are pKa 25. Our alkenes pKa 45. Our alkanes pKa 60. Okay. All right. Questions on that? Okay. Okay, very good. Know your electronegativity trends right here. It affects polarity, acidity, basicity, and leaving groupability. The weaker the base, the better a leaving group. Okay, the weaker the base, the better the leaving group. All right, and then nomenclature, covering basically all the chapters except for chapter 5. So alkanes, alkynes, alkenes, and cyclic compounds. Remember, you have cis and trans in your cyclic compounds and also bicyclic compounds. Brackets. Don't forget your brackets. Alcohols, ethers, and epoxies. Remember, they're called oxiranes. And if you name them, depending on how you name them, you have to start with the oxygen or not. And then cis and trans, if you only have 2 things in your alkene, and E and Z right there. So that means that we have all of the rules we need to really name everything up to alcohols. It's that same, there's a nomenclature review on Canvas under there. It goes all the functional groups plus their priority. And so who has the highest priority or the lowest priority. So look at that. And And again, when you assign priorities, there's actually 4 rules. There's 3 listed here, but it's atomic number. If that solves your problem, you're done. What's attached to it? If that solves your problem when it's done. If it has a double or triple bond, that atom it's bonded to counts for each of those bonds. And of course, the 4th rule is isotope. Heavier isotope has higher priority. Okay. So again, really the first rule used to be just find the longest chain, but we have to change that to find the longest chain with the highest priority functional group. And so far, our highest priority functional group is alcohol. Okay, but we have to make sure we know what we have the nature of our double bonds. We have to know if there's double bonds or triple bonds. Add your substituents number. Ooh, for alkenes, you want to have the alkene have the lowest numbers possible if it's in the main chain, and both carbons have to be in the main chain. Sorry, mute for now. Okay. So make sure you remember that rule. That one can be tricky sometimes. And then of course, alphabetize, not using di, tri, tetra, but definitely with iso on there. Okay. Know your alkyl functional groups and their names. You know, the sec-butyl, isobutyl, tert-butyl. Okay. Iso actually, because it's part of the word, it's not italicized. The italicized word doesn't count. Only the ones that aren't there. So the isopropyl and the isobutyl do count for alphabetization, but sec-butyl doesn't. It counts as a theme. Okay. Remember your ring nomenclature. You want to have the smallest number of things. If you only have one thing on the ring, that's 1. Okay, so you want your smallest number. With cycloalkenes, you have to label 1, 2 through the double bond. 1 carbon of the double bond is 1, 1 carbon of the double bond is 2. So in the case of this one here, we can actually say this has to be 1 because it's double bond and it has something on it, which means this is number 2, 3, 4, 5, 6. So that's how you do it. And on this one has to be 1 because it has something on it, which makes this 2, 3, 4, 5. Okay, so make sure you follow that rule. That's one of the really subtle little things there, but that rule is important. Okay, and bicyclos. Okay, remember the trick about easy way to draw your bicyclos is to start with your bridgeheads, and then you go through your brackets. 3, 1, 2, 3, 2, 1, 2, 1, like that. So know your brackets. You have your largest one first. So you're going to have 3, 2, 1, 1, 1, 1, 1, 1, 0. Remember, 0 is if the bridgeheads are connecting each other. So you're going to look at the parent name, which is the total number of carbons, and then the bridges, and identify the bridgeheads, and then add substituents as needed. Now remember, when you're numbering, you have to start at a bridgehead and go around the longest one first, and then your last bridge, then your second one second, and then your last bridge is that last. Actually, that's 7. Sorry, 7. Okay, so you'll have to just jump over to wherever your last bridge is for the other numbers. Okay, questions on that? Okay. Degrees of unsaturation. Remember this equation here, right here. We're looking for 2n plus 2 minus 2x. Okay, n is the number of carbons, and you're looking for x. X is your degree of unsaturation. Okay, so if you have 1 degree of unsaturation, you have at least 1 double bond or a ring. So in this case here, we have a ring, which is 1 degree of unsaturation, and 2 double bonds, that's 2 more. So that has a degree of unsaturation of 3. Okay, Now, remember, when you have oxygen on there, it doesn't count. You just don't worry about it. Okay. If you have halogens on there, they count as hydrogens because they're only bonded once. If you have nitrogen on there, you subtract 1 because it only bonds 3 times. And then, therefore, that allows you to be able to calculate your degree of unsaturation with any element. All right. So star that slide. There. All right. Know your cyclohexane conformers, chair 1, chair 2, and be able to draw it as a Fisher projection, not Fisher projection, Newman projection. Newman projection. Okay. All your axials become equatorial when you flip from one chair to the other chair. All of them flip positions. So you want to have the most stable one with your largest group in the equatorial position. Okay. All right. Chapter 5, chirality. Dun, dun, dun. Coming to a test near you. Okay, so in that we are looking for, is it chiral? 4 different groups on it? Might be. So let's go through there. Now you can get tricked though, because if you have 2 chiral centers and there's a mirror plane somewhere there, it's meso. So it becomes a chiral. But always look for that. This is where when you have 2 of them, the diastereomers are with 2 or more. And remember, you'll have 2 to the n, however many stereocenters you have, isomers. So if that's 3, you'll have 8 isomers possible. Okay. Know that how easy it is to draw your enantiomers with that mirror plane, and then flip one group and draw your next diastereomer and its enantiomer. That's why we love the Fisher projection. Okay. Okay. So, and know that, you know, these 2 right here are diastereomers, but these 2 right here are enantiomers. Know the difference between enantiomer and diastereomer. Okay. And then, of course, always look for your mirror planes. And even if you have to redraw it, rotate it around so it looks to have 2 of the groups in the same place, so you can look for that there. All right, Fisher projections. Okay. Don't forget that things going horizontal or sticking out at you. Anything in the vertical is going away from you, and you always want your longest carbon chain going vertically. Longest carbon chain going vertically. Okay. Then once you have that, you can easily swap around between the enantiomer and the diastereomer by just either drawing the mirror image or swapping one of the stereocenters. That gives you your next set of enantiomers. Okay. All right, and then of course our rules are the same for E and Z as they are for R and S, right? Figuring out priority. But in E and Z, you figure out one half of the molecule and the other half of the molecule. You only have to prioritize to 1 on both sides. We have to do all 4. And then when you have all 4, you want to get the lowest one away from you, pointing away from you, so you can get your R and S perspective. R is clockwise, S is counterclockwise. All right. So that's the stereochemistry. That wasn't too hard. Also remember that it rotates light. Remember that one enantiomer will rotate it one way, X degrees, and the other one will rotate it X degrees. Yes.
Did you say pertaining to that, that when it comes to the direction that it rotates light, it's not always R rotates light and D?
No.
S is
Yeah,
not
there's
always
no correlation between what you labeled it, because we're naming it, and how it actually is, the chemical exists.
Okay, so R could be L.
It could be either way. It could be dextrorotatory, laboratory, or if it, so there's no way to tell until you measure it. All right, so know the difference between thermodynamics and kinetics. Okay, so kinetics is all about the speed of the reaction, right? And therefore, it's going to try to take the fastest, simplest route. Thermodynamics is all about the beginning and the end, right? It doesn't matter how many steps you did going from here to here. The thing is you gave off heat, so you have a more stable concept, okay? Know that you have an activation energy to get to a transition state, right? The tops of these are transition states. This is an intermediate. This is a transition state. That's a product. Know the difference between transition state and products. Your activation energy is necessary to get to the transition state. Your intermediate typically has a lower activation energy to get to its next transition state, okay? Exothermic, of course, gives off heat. We have a negative energy here. Endothermics have a positive delta G or delta H enthalpy. Okay. And be able to recognize a one-step reaction or a two-step reaction by its reaction coordinate diagram. Let's see, first order reactions, like an SN1 or E1, we wait around for a bond to break. Remember, there's only 5 things that can happen in a mechanism. Add a proton, add a proton, take a proton away, react an electrophile with a nucleophile to make a new sigma bond, rearrange or break a bond to form a stable or a charged intermediate. So in this one, we're breaking it. And we're giving it, because we have to wait for it to break before it forms that intermediate, we only care about the concentration of that substrate. So it is first order, one thing and all that. And remember, if you look at our rate law, there's a 1 here, and so there's only 1, and so that's first order. In the case of our second order, we have a probably concerted reaction. We have the reaction of a nucleophile and electrophile to form a new sigma bond. And therefore, it's important for both of those things to be here. So we have a 1 here and a 1 here, so that makes it 2. So it's a second order. So think SN2, think E2, addition reactions that don't form intermediates. A lot of the addition reactions form intermediates. Radical reaction is second order in the propagation step. Because remember, you have to have your 2 things together to either abstract a hydrogen or add a. So I like to do this to make you think about, we only talked about it in 1 chapter, but every reaction does have a rate law. Okay. And anytime you have to have something add to something, they have to both be there at the same time. So you're looking at a second order. Okay, let's see, what else do we have? Stabilities of carbocations and radicals. Luckily, they follow the same trend, okay? Our benzylic and our allylic cations, actually, I think this figure is wrong. I think these are more stable. Come on. I think these are more stable than a carbocation because of delocalization. So double check that. Again, if you're never going to make methyl or a primary, only going to make the allylic, the secondary, and the tertiary, and the benzylic. And what's the problem with carbocations? If they can rearrange, they will. If you have a secondary, it's going to rearrange to a tertiary. Okay, it won't go from a secondary to secondary, but it will go from a secondary to a tertiary. If you already have it on a tertiary carbon, it's not going to move you. So there you go. And there's 2 ways to shift, with a hydrogen and a methyl group, or what's the third way? Ring expansion. All right. So ring expansion. Ring expansion is most common in 3, 4, and 5 membered rings. Once you get a 6-membered ring, there's no ring expansion because
Stable.
there's no ring strain. No ring strain. Okay, so 3, 4, 5s will all have ring strain, and therefore they will do that movement. All right. 3, 4, yeah, okay, it's on there. Yay, all right. So SN1 reactions, of course, first order rate law, favored by poor nucleophiles, water, methanol, ethanol, acetic acid. Waits for the carbocation, only works with the tertiary substrate. Okay, it can sort of kind of work on a secondary substrate, it is really, really slow. Okay, SN2 is all about good nucleophiles. Things with a negative charge plus nitrogen are pretty good. And there's 3 classifications of nucleophiles: good nucleophiles, fair nucleophiles, and poor nucleophiles. Be able to identify all of those. Obviously, the good nucleophiles tend to be the ones with negative charges, but then we have things like fluorine and chlorine, which are smaller, and they actually are in the fair. Okay, bromine and iodine are good nucleophiles because they're polarizable. So remember those things. Leaving group effects and solvents. Specifically, the halogen series. In polar protic solvents, it can support both the cation and the anion. In polar aprotic solvents, it doesn't support the cation or the anion group. So know the trend for that. We should all know the SN2 is a one-step reaction, therefore second order rate law has one hump on its diagram. Okay, it's no carbocations, which means no rearrangements. However, there is inversion of center, inversion of stereocenter. So it has that to be important thing, addition there. Let's see, reactivity, methyl goes faster than secondary, goes faster than, I'm sorry, methyl goes faster than primary and secondary because of sterics. You have sterics. And you hardly ever get a tertiary to go. SN1 is you form that carbocation, therefore you just have to break a bond first. You have 2 humps in your reaction diagram. You have to have a pretty good leaving group, iodine, bromine, chlorine, and you have to have a polar protic solvent. Okay, and then you have to have a very poor nucleophile, something neutral, probably water, ethanol, etc. And of course, tertiaries react faster than secondaries, and primary methods pretty much don't react at all. All right, nucleophilicity. Remember, nucleophilicity is a kinetic issue. Basicity and acidity are thermodynamic because they're in equilibrium. So all we're looking for is that we are looking for these things to attack, so it's a kinetic feature. Notice that all of our good nucleophiles have negative charges. Okay, all of our neutral, some of our neutral ones actually could be good nucleophiles or fair nucleophiles as well. For example, this nitrogen and these phosphorus, these are pretty good. Okay, most of the time we don't have to put our counterions, but on the exam they might have counterions. So just pay attention to what actually was reacting. And then our halide series here. Figure out a way to remember this, is that in a polar aprotic solvent, fluorine is the best nucleophile. Small charge, not supported. Fast. Okay, more nucleophile. In polar protic solvents, you now look at polarizability. So iodine's best. Okay, so make sure you have that trend down. Okay. That looks like a duplicate slide. Nope, okay. So most of the times there'll be a balanced equation, but sometimes they'll leave this part out here. We did do homework on that, so we should remember that. Whenever you have a nucleophile attacking an electrophile, you end up with a neutral product. You started out with a neutral substrate and you attacked it with an anion to create a new sigma bond with those electrons on the anion, and therefore you have a neutral product. However, if you attack with a neutral species, you end up with a charged product and you need to lose a proton somehow. Okay, so you end up with this charged intermediate here, then you're using your poor nucleophile, or moderate nucleophile here as our base, and we get to our neutral product only after proton transfer. Okay. So let's see, E1, E2, okay. E1 is always in competition with SN1. So it only happens with poor bases, water, ethanol, methanol, okay. So we have to do our E1 reaction, form our carbocation first, then lose a proton with a weak base, okay. So in our E2, we have our strong bases, okay. So ethanol, isopropanol, alkoxides, those kind of things. Now remember, methanol can act as a good nucleophile. But if you have it on a secondary or tertiary substrate, it's going to do the elimination reaction. Primary substrate, it might do the substitution reaction. So make sure you take your sterics and look at your table again. We have a Zaitsev's rule and Hoffman rule. Zaitsev's rule said you're going to form the more stable one, if at all possible. But Hoffman says if you have a super bulky base, you're going to make the less stable, you're going to make the one that is more on the outside of the molecule. Okay. And again, the more substituted, the more stable. All right. Now, we looked at a specific case in cyclohexane, where you can form your product only when your hydrogen and your leaving group are anti-periplanar to each other. Okay, so they have to be anti-periplanar to each other. They both have to be in axial positions. If you cannot get a hydrogen in an axial position on the more stable side, it's not going to eliminate there. So you have to look where that axial hydrogen, oh, it's going to be on this side because that's where the axial hydrogen is, and when my halogen or my leaving group is in there. Oh, and remember, X is usually halogens, but we just introduced a good leaving group, OTS. The tosylate makes it a good leaving group. So alcohols are horrible leaving groups, OH is a horrible, but now we have a new one. And this is just as good a leaving group as iodine or bromine. So you'll start looking for that as a leaving group as well. Okay. So again, with our bromine in this axial position here, we only have methyl groups. So it can't even do any elimination reaction. It's just not going to react at all. And no reaction is sometimes the right answer. Okay. I harped on this table quite a bit. Go ahead and download another empty one and talk yourself through it and then double check it. Again, we can get substitution with methoxide and ethoxide in primaries, but after that, they'll do E2. And notice all these do E2 when you get to big bulky bases. And then, of course, our carbocations with our tertiaries here. Even with good nucleophiles, we still have to wait for that carbocation to form because there's just no way to get the nucleophile in at 180 degrees from your leaving group. Okay. Strong nucleophiles, weak nucleophiles. Now remember, there's a couple in the intermediate ones. In the table in the book, there's intermediate ones as well. Okay. All right, let's see. All right, questions about E1, E2? So that was chapter 7. And then in chapter 8, we learned addition reactions to alkenes. Okay, so we learned how to make alkenes, and then we learned how to destroy them. So know that your reagents can be selective. Okay, stereoselective and reacts at certain points, right? So in this case here, we're looking at how to make alcohols or reactions of alcohols. And so this was actually covered in chapter 7, but I wanted to draw attention to it, that this is in chapter 7, and then these are in chapter 11. Notice that we can do substitution reactions based on the type of nucleophile it is or whether it's a base. So in this case here, we converted our alcohol to a halogen, either with the acid in an acid catalyzed substitution reaction, or with thionyl chloride or bromine tribromide, phosphorus tribromide. Now, that just gets us to our leaving group here. Now, whether it's a good nucleophile or a base tells you whether you're going to do substitution or elimination. Okay. In the case of an E1, right here, we get E1 elimination for primaries and secondaries in the acid catalyzed. Okay, because it protonates the alcohol, turns it into a good leaving group, and then it can rearrange. Primaries don't do that. Primaries don't form the carbocation. It's an SN2 reaction. Okay, to form that, or an E2 reaction to form the double bond. Okay. Okay. So now in chapter 8, we're looking at several different mechanisms. There's only like 5 different transition states available to us in there. Okay, the first one was with the hydrohalogenation or hydration. They're pretty much the same mechanism where we have attack by the alkene onto an acidic proton and forming a new sigma bond with that hydrogen, allowing for the formation of a carbocation that then is very reactive toward this very weak base. So it's a very weak base, and so we're going to do the addition. Okay, so that's the same mechanism for water, acid catalyzed hydration with water. Halogenation, we get that anti-configuration because forming that little oxonium, or bromonium or chlorinium cation, that means we have anti-addition. Anti-addition. Notice you get a mixture of anti and syn addition here because you form the carbocation. Remember the shape of the carbocation, top, bottom. Also, it's going to be racemic. All right, this is just the mechanism for that. Notice that even though we have our alkene here, depending on where the groups are, we see that we get anti-addition, okay? All right, in this case here, our R groups are trans to each other. It's going to give rise to a certain number of products that is going to be different than the one that is in the cis alkene, okay? So the regioselectivity of where that next bromine can come on, and note it can go on one or the other, so it's going to give you a pair of enantiomers. But in this case here, it actually turned out to be a meso compound. So look for where that thing is, and know that you can get pairs of enantiomers depending on whether the first attachment was on the top of the double bond or on the bottom of the double bond. So this alkene right here, we can do a number of different things with it. We learned in chapter 11 that we can make ethers using these same reagents here that we had. We're going to make our acid catalyzed hydration. It's going to give us our most substituted like carbocation rearrangement. And we can make that ether in that same position by carbocation rearrangement. We don't want it to rearrange, but we know where we want to put the where we want to put that. We're going to add the mercury to this side, right here. And then we're going to keep it there until we reduce it off, giving us our secondary alcohol only by attack of the water in the second step. Or we can do an attack with an alcohol. Change water out for an alcohol, and now you have an ether. And of course, the only way like primary alcohol is with your boronation, oxy-deboronation. You have to add syn addition, just like hydrogenation, syn addition, and then oxidize off the boron to give us our OH group. Okay, then this table is the beginning of the slides in that section. It sums up most of those stuff in there, including our ozonolysis is the only way to get to our dialdehydes or aldehyde and ketones. But if you don't care, you want carboxylic acid, you're going to use permanganate hot. You get diols from cold permanganate and osmium tetroxide. We can get all of these different reactions. Notice these are the same mechanism right here. This is a different mechanism. This is the same, these two are the same mechanism, sorry. But we have more of another, we have more water around. And then these two are two different mechanisms here. So know that they are different mechanisms. That gives you your selectivity and your regioselectivity. Okay. And let's see. You can make, how to make alkynes. You can't make an alkyne with just hydroxide. You have to use sodium amide. And And you have to have two halogens. They can be geminal on the same carbon or vicinal in the same area, one carbon apart to do it. And you have to use two equivalents of sodium amide, one for the first equivalent of acid, HCl, and one for the second. Once you have that, you can then use it as a nucleophile. So here's the vicinal dibromides. If you have a terminal alkyne, you can use it as a nucleophile by deprotonating it with that sodium amide. If you don't have a terminal alkyne, if it's in the middle of the chain, you can't use it. And then all you're looking for is, well, how can I turn it into an alkene, or do I want a cis alkene or a trans alkene? Because you have to choose your reaction. Again, we can make the double bond, and we did this in those multi-step synthesis. You're going to see in multi-step synthesis where you're starting with a double bond, but they want a triple bond. So you just have to add bromine across it. That'll give you your vicinal dibromide. And then you use two equivalents of the sodium amide to make your triple bond. And let's see. Oh, and then we can add HCl across a triple bond. If we have one equivalent, we're only going to add it once. We're going to get our alkene. But notice it's the same mechanism as hydrohalogenation of an alkene. It's just we're ending up with a double bond because we started with two double bonds. And we're going to add across one of them, keeping the last one. Okay, so we're still in chapter 8. So if you only add one equivalent with the acid, you can stop at the alkene. If you add a second equivalent or excess, you'll get to the vicinal, no, not the vicinal, geminal dihalide, because now you have the first one's going to add just on there somewhere if you have an internal alkyne. But now you have a carbon with one more hydrogen on it than the other one. The other one has the halogen on it. Therefore, it's going to follow Markovnikov's rule and put both hydrogens on the same carbon and both halogens on the same carbon. Okay, so it's, and then if we have one equivalent, we can stop at the dibromo compound. Notice that it is going to give us the trans isomer. Okay, because when you put the first bromine on top, the other one has to come from the bottom. It's going to give us our trans isomer. And by adding another equivalent, you get to your tetrabromo or tetrachloro. So the mechanism on that is the same as for alkenes, but you have to do it twice. Okay. And then, of course, getting rid of your alkyne, getting it all the way down to a hydrocarbon, that's easy to do. Getting the cis alkene, you use your Lindner's catalyst or the nickel boride. But if you want the trans alkene, you have to use the dissolving metal reaction or sodium or lithium in there. Remember, that's a different mechanism. You're forming a radical anion that's acting as a base. We're going to transfer a proton and we get our trans isomer. It's the only way to get a trans isomer. Then, of course, once you have a terminal alkyne, you can use it as a nucleophile. Right here with a good SN2 reaction. All right, questions on that? So at least we're starting to remember these, okay? Because we've done a lot. I mean, we've learned a lot. So ozonolysis with an oxidized, well, ozonolysis, when you have an ozonolysis with an alkyne, okay, there's no way to stop at the alkyne because there's no hydrogen there. It always oxidizes it down to the carboxylic acid. Okay, it has to break these bonds and start adding oxygen to there. And we can also do it with permanganate, again, hot. Okay, so ozonolysis cleaves alkenes and alkynes. Okay, and now if you have a terminal alkyne, remember, count the number of carbons. That was one of those retrosynthetic things. Count the number of carbons on the beginning and the end and see if you gained carbons or lost carbons. If you gained carbons, you have to do some kind of SN2 reaction with a carbon nucleophile. If you lost them, you probably did some kind of oxidation. And if you only lost one, that means you probably gave off CO2. All right. So that was really cool. So let's see. There's only 5 things to remember about radicals. Okay. Initiation, propagation, and termination. So no radicals, forming radicals, initiation. Radicals reacting to form radicals, propagation. Radicals reacting together to form neutral species, termination. And you only do 2 things: abstract a hydrogen or add across a double bond, generating another radical. Okay. And then let's see, the other thing about that is adding a radical generator to HBr changes the reaction from Markovnikov's addition to anti-Markovnikov's addition. So radicals are useful for that as well. And then, of course, you can use NBS or bromine for allylic or benzylic halogenations, because it, again, generates radicals. Right? Our radical stability, benzylic and allylic are the most stable because of resonance, and therefore you have to pay attention. The ring itself will never actually get the addition reaction on there because it wants to stay aromatic, so it'll only do it at that benzylic site. However, when you have the allylic, you are going to have some react on either end. And again, you can form vinyl and methyl radicals. They're not that hard to form. The energy difference between them and stability is not that great. So we do form primary radicals very easily, but they're not as stable as the others. Let's see. We can do mostly bromine and chlorine on here. We'll see that in this radical halogenation. And remember, chlorine is less selective. And you have to look at the product ratio based on the reactivity ratio. Okay, bromine is more selective, and therefore it'll typically give you the more substituting product, the tertiary halide, if possible. And then, of course, our anti-Markovnikov's addition. So if we have any benzylic hydrogens at all, and you hit it with light or HNU there, you're going to get that benzylic halogenation first. If you have a alkene here, you're actually going to get a mess of reactions because you're going to get some of them here. Bromine's going to add here. And so you're going to get some dibromo compounds, some monobromo compounds, some with alkenes, some without alkenes. So we avoid that by using the NBS with peroxides. And that gives us our allylic radical. Our allylic radical is always going to give us our halogen, 1 carbon off our double bond. Now notice this is symmetrical here, so it's useful. Remember that if you have rings, that can be a synthetically useful thing without selectivity because they're all equal. And so you're only going to get that. And then, of course, we can do that same thing right here. But notice you're getting addition at one end of where the radical forms and at the other side. So you actually get a mixture of products. Mixture of products. Okay, let's see. So when you have alkanes, the halogenation is going to be primarily at the most stable site or the most substituted site because the tertiary carbocation is more stable and forms faster. The reason it forms is it's easier to form and therefore it forms faster. So it's a kinetic issue. With allylics, you want to do your NBS and peroxides. And if you just do it bromine in the dark, you're going to lose your double bond. That was from the chapter 8. And then, of course, we can add HBr across there with light, anti-Markovnikov's, in the dark, Markovnikov's. Notice that it actually formed the carbocation and moved. So we actually form the tertiary right here. We get the primary with the peroxide. Okay. All right. Oops. Oh, okay. Okay. I'll pick up here on quiz on chapter 11 on Wednesday, followed by the rest of these slides, and I'm going to do some problem solving, some multi-step synthesis, just to kind of tie it all together. We'll do reactions for the whole for all the chapters. Okay. All right. Thank you very much. See you on Wednesday. Go ahead and stop sharing. I'm going to stop recording.